Hey, welcome to the Explainer. Today, we're going to dive into the hidden science that explains why things stretch, bend, and even compress. We're talking all about elasticity, stress, and strain.
So, have you ever wondered about this? You stretch a rubber band, let it go, and bam, it snaps right back. But you bend a paper clip, maybe a little too far, and it just stays that way, permanently deformed. Well, that very difference is the key to everything we're going to explore today. It's all about that line between an object's ability to bounce back and its breaking point.
All right, so here's the game plan for today. We're going to start with the absolute fundamentals, the big ideas of stress and strain. Then we'll break down the three main ways things can deform. That's stretching, shearing, and squeezing. And finally, we'll connect it all back to the world around us. Let's get into it.
First up, let's talk about stress and strain. You really have to get these two concepts down because they are the foundation for everything else we'll discuss. Think of them as the universal language that physicists and engineers use to talk about how materials behave when you push or pull on them.
Okay, so at the most basic level, anytime you apply a force and an object changes shape, that's called a deformation. And it happens more than you think. I mean, right now, as you sit in your chair, you're deforming it, even if you can't see it with your own eyes. Now, for small changes, materials are what we call elastic. It's like they have a memory, and they snap right back to how they were before the force was applied.
And this elastic behavior? It follows a really simple, elegant rule called Hooke's law. All it says is that for those small deformations, the amount an object stretches or compresses, that's our delta L there, is directly proportional to the force you apply. So if you double the force, you double the stretch. It's a really straightforward relationship.
Now, to really make this useful and universal, we need two key terms: stress and strain. And here's the deal. Stress is the force spread out over an area. It's what you do to the object. Strain, on the other hand, is how the object responds. It's the fractional or relative change in its shape. By thinking in terms of stress and strain, we can compare, say, a tiny steel wire to a massive steel I-beam and understand their properties in the exact same way. It's incredibly powerful.
All right, let's get into our first specific type of deformation. We'll start with the one that's probably the most intuitive for all of us. Changes in length, like stretching a rope or compressing a pillar.
So every material has a special property called Young's modulus, which we represent with a capital Y. This number is basically a measure of how stiff that material is. It's the ratio of the stress you apply to the strain that you get as a result. So if something has a really high Young's modulus like steel, it means you have to apply an absolutely enormous amount of stress just to get a tiny little bit of strain. It's just incredibly resistant to being stretched.
Okay, let's put this into practice and see how it works with a real-world example. Imagine a huge steel suspension cable at a ski resort. It's over 3 kilometers long. How much does it actually stretch under a massive force? Well, step 1, we list everything we know. We've got the force, the original length, the area of the cable, and that all-important Young's modulus for steel. Step 2, we grab our formula, which is really just a rearranged version of that stress over strain relationship. And step 3, we plug in the numbers and wow, the cable stretches by 18 meters. Now that sounds like a lot, right? But it's actually less than 1% of its total length, which just goes to show you how unbelievably stiff steel really is. Okay, moving on to our second type of deformation, shearing. Now this isn't about pulling something apart or squishing it. This is about applying a force sideways, parallel to a surface.
The best way I've found to picture shear is with a deck of cards or maybe a thick book. Imagine it's flat on a table. If you push the top cover sideways while you hold the bottom one perfectly still, the whole thing kind of leans and distorts. That sliding action, that's shear. The force is running parallel to that top surface.
And you guessed it, just like we had a special number for stretching, we have one for this too. It's called the shear modulus, and we label it with an S. This tells you how well a material can resist being bent, twisted, or sheared. So a high shear modulus means the material is super rigid and won't distort sideways very easily.
So let's run the numbers on this one too. Let's say we have a steel nail holding up a picture frame. How much weight can it actually support if it only bends sideways by a microscopic amount, like 1.8 micrometers? Again, we just follow the steps. We identify all our knowns, including the shear modulus for steel. Now this time we rearrange the formula because we want to solve for the force. We plug everything in, and we find the force is 51 newtons. That's the weight of a 5.2 kilogram object. That's pretty impressive for a bend that's so tiny you would never, ever be able to see it.
All right, that brings us to our third and final type of deformation, changes in volume. This is what happens when an object gets squeezed from every single direction, all at once, uniformly.
Just picture something at the bottom of the ocean, right? The incredible weight of all that water above it is creating a uniform pressure, pushing inward on every square inch of its surface. It's trying to shrink its total volume. That's bulk stress.
And of course, there's a modulus for this too. It's called the bulk modulus, or B, and it measures how much a material resists being compressed. What's really fascinating here is that both solids and liquids tend to have incredibly high bulk moduli. This is exactly why it feels impossible to compress water in a bottle. You are literally fighting against the immense forces that keep atoms from crashing into each other.
Okay, let's take a look at this table together, because it really tells a story. You can immediately see the huge differences. Look at steel. Its Young's modulus is 210, while bone is down at 16. That's why steel is so much stiffer. And also check out water. It doesn't even have a Young's or shear modulus. That makes sense, right? You can't really stretch a bucket of water. It only has a bulk modulus because it resists being compressed.
All right, time for a quick pop quiz to see if you're following along. Just looking at that Young's modulus column, which material is harder to stretch, steel or aluminum? If you said steel because its value of 210 is way higher than aluminum's 70, you are absolutely right. It's about 3 times stiffer.
In this chart, this does a fantastic job of showing that even a single material, like steel, responds completely differently to different kinds of stress. For steel, it's hardest to stretch it, then a bit easier to compress its volume, and easiest of all to shear it. Each modulus tells you a different part of that material's story.
Okay, so we've covered the big 3 types of stress, strain, and their moduli. Let's take a step back and wrap this all up by talking about why any of this actually matters in the real world. Believe me, this isn't just some abstract stuff for a physics textbook. It is everywhere. Engineers rely on these principles to build skyscrapers that can sway safely in the wind and bridges that can flex as cars drive over them. In our own bodies, the stretchiness of our tendons and arteries is absolutely crucial for us to move and survive. It's even in nature, when water freezes and expands, it's unleashing forces so powerful they can crack solid rock.
And it affects our own bodies in ways we might not think about. I mean, take this quote from our source material. It points out that the natural curve in our spine actually creates shearing forces on our vertebrae. Understanding that helps doctors and physical therapists figure out why certain postures can lead to serious back injuries. It's a direct biological consequence of shear stress.
So, I'm going to leave you with a final thought, a little challenge. Now that you know the language of stress and strain, just look around you. Think about the chair you're sitting on right this second. Your weight is creating compression in its legs. If you wiggle around, you're creating shearing forces in all the joints. And the material itself is resisting a change in